Hi, I'm Ken the Metal Professor, or more specifically, Ken the recently retired Metal Math Professor. Here's how my life in retirement is going. Earlier today, I woke up around 8 or 8:30, came in here and put together an audio file for a radio show that I do. Then I exercised while watching some New Japan Pro Wrestling on the television. And I went to go see that new movie, Smile. And then I went shopping. And then I decided, before we get into the weekend, I should do another one of these recently on Math Reddit videos. So I dove into the R Calculus subreddit and picked out a couple of questions that shouldn't take too long, but sounded a lot of fun to talk about. So I've got one from the user Turbo Codone, which is about the equation of a tangent line, and we'll be throwing around a product rule and a little bitty chain rule in the process of doing derivatives there, and Melancholy Cupcake on that same subreddit with a question about a related rates problem. Those are always fun. So let's take a look at the tangent line problem first. I'm not going to solve the problem exactly as it was stated. I'm going to do a similar version so that this solution could be adapted for the one that was actually posted. But the question was very standard. Find the equation of the line tangent to this function, x cubed times e to the 2 minus 3x at x equals 1. So as you all have memorized to a T, this is what the equation of a tangent line looks like. Now that's gross. And when people see this, they go, this is new. I don't like it. But it's not new. Okay, so first of all, let's undo all of the noise. First, I'm going to take this f of x 0 term and subtract it to the left. And then I'm just going to remember that all these f of x business things, they're just y coordinates, right? And when I'm talking about a tangent line, the slope of that line comes from this derivative term. So this is just a slope. So everything in here is just the good old-fashioned point slope formula for the equation of a line in disguise. It's just been buffered up to put in f of x instead of y. It's taken the generic slope and put in place the fact that we are specifically looking for the value of a derivative to tell us the slope. But when it's all said and done, I don't really try to remember this top version. I just go back to the old-fashioned equation of a line and understand. I'm going to have to figure out the point that's in question, and I'm going to have to remember that the slope of the tangent line at this point is going to come from the derivative of the function. So really, we're just doing this. Okay. Now, for this given function, we need to find the full point on the line, whichever alphabet soup that you're using to describe it. The x coordinate was given, we've got to find the y coordinate, and for this function, that y coordinate is pretty easy. It's 1 cubed times e to the 2 minus 3 times 1, or 1 times e to the negative 1, which is 1 over e. E is a little bit less than 1/3, or a little less than 3, so 1 over e is a little bit bigger than 1/3. So this is the coordinate of our point on the line. Of the 3 numbers we needed to calculate or to generate the equation of the line, we already got 2 of them. Now we need the slope of that line. Okay. To do the slope, we are going to need the derivative of our function. This will require the product rule, and it will require a little bitty chain rule. So as a reminder, this is how the product rule works. If you take the noise out of it, it's just the idea that the derivative of a product of 2 functions of x, each piece gets its turn taken under the derivative sign, while the other piece just sits there twiddling its thumbs. So the derivative of x cubed e to the 2 minus 3x, well, here in the first term, the x cubed is just sitting there hanging out. We do the derivative of the other part, and then we switch places. The derivative of e to the 2 minus 3x requires a teeny tiny chain rule. It is e to the 2 minus 3x times the derivative of 2 minus 3x. And here I've just put in the derivative of x cubed. Then I've evaluated this derivative of 2 minus 3x, and now I recognize this is a sloppy mess, but hey, I can factor an x squared out of each term, I can factor a 3 out of each term, and I can factor the e to the 2 minus 3x out of each term. And so I can clean this up quite nicely to look like this. And now I can say, whoops, that stupid bar. I always forget to not let my mouse creep to the lower part of the screen and activate that PDF bar. Maybe there's a way in the settings to turn that off. Anyway, conveniently, we're asking for the slope of this tangent line at x equals 1. So we want to plug x equals 1 into that derivative, and that gives us 0. Okay, so the point, or the line in question is going to be thumbtacked to the point 1 over 1 minus e and have the slope 0. So pick whichever format of this equation of the tangent line you like. I'm going to pick the third one. I know my point has an x-coordinate of 1, a y-coordinate of 1 over e, and I know my slope is 0, and we shake this out to the line y equals 1 over e, which turns out to just be a horizontal line. Here is a picture of this scenario. The red curve right here is the function, and right here at x equals 1, we come up and find this tangent line is a horizontal line at y equals, well, that is 1 over e, a little bit bigger than 1/3. So everything seems to shake out. So again, the original question had a slightly different function, but the structure of the function was the same. Whoops, you don't need to see that. You want to see this. So there you go. I hope that helps. All right, second problem, related rates. I like these. So here's the statement of the problem as posted. A softball diamond is a square whose sides are, typo there, not going to go fix it, whose sides are 18 meters long. That seems kind of short, but maybe it's right. Suppose that a player running from first to second base has a speed of 7.5 meters per second, and at the instant she is 3 meters from second base. At what rate is the player's distance from home changing? Okay, so let's think about the general strategy for related rates problems. First of all, these are called related rates because you're going to relate rates of change to each other. You're generally given a scenario which boils down to a geometry. You're going to end up drawing, and you will draw a picture. It's going to be a circle, a triangle, or a rectangle. Fundamentally, that's 90% of your related rates problems. Involves those shapes. However, parts of the shape, some dimensions of the shape are going to be changing. You're going to know or be told one rate of change, and you're going to have to figure out the other rate of change. So you are relating rates of change. But it's all just about simple geometry. So, draw a picture. Dang it. On that picture, list out the data that you have and identify in particular if I've labeled the diagram with X, Y, and Z. Somewhere in the question, there's going to be a prompt that says, how fast is this thing changing? Well, that identifies the rate of change that you need to calculate. Figure out which one it is based on the variables that you're giving. Again, you're going to end up with a circle, a triangle, rectangle, or square, something like that. Maybe you're working with 3D shapes and you're looking at a sphere, a cylinder, whatever it is. It's going to be a simple geometric shape. There's going to be some fundamental known formula about the geometry of that shape that you'll bring into play. We're going to find the derivative with respect to time of both sides of that equation. What's happening here is you're just, the difference between calculus and everything that came before is that everything that came before was static. Here's a shape. What is the radius? Here is another shape. What is the volume? In calculus, we learn how to turn on the power switch and let some of the dimensions start changing so we can ask how fast are these things changing. That power switch is the derivative with respect to time. Okay. Now, we turn on the power switch by taking a derivative of whatever geometric equation we have, and things are changing, and we're going to go click and take a snapshot. And at that instant, we're going to do all of our calculations. And in those calculations, we're going to throw in the known values. We're going to find and identify the one value that we're being asked to compute. There's probably another value or two that we have to be clever about how to figure it out, but we can do that. Okay, so here is the softball problem. I've drawn a picture sort of already. my attempt at half of a softball diamond. So here is home plate down at the bottom. Here is first base. Here is second base. And here is the runner speeding towards second base at a rate of 3 meters per second. Okay. What diagram did this make? It made a triangle. Now, here's the fun part. Even though we're talking about home to first to second, the legs of the triangle that we're interested in are not home to first and first to second in its entirety. The pieces of the triangle we're interested in are home to first, first to the runner, and then the runner back to home. Now that's still a right triangle. We don't even need to label this side because that length is fixed. We're asked to calculate the rate of change of this distance, the distance from the runner to home. So let's call that capital D for distance. I don't want to call it lowercase d because when we start writing derivatives, little d is going to be tied up in the derivative notation, and you don't want to be asking for the derivative of little d because that's really confusing. So we'll call it big D. And I'm going to be clever and call that dimension R for runner. We happen to be told the rate of change of this. This is the speed that the runner is moving from first to second. So we're told that this rate is 3 meters per second. That is dr over dt. dr is a distance, dt is a time, distance over time in the units. It all works out. Okay, we are being asked to compute the rate of change of this. Right, this is what we don't know. Okay, now if I just said, forget that it's a related rates problem, do you know any formulas that tie together little r, big D, and 18 for this picture? And you say, of course there's a formula. It's the Pythagorean theorem. This is a right triangle. Okay, and that's how we get our hook into this problem. Now, generally speaking, when you have the Pythagorean theorem in play, x squared plus y squared equals r squared, when all three distances are changing with respect to time, how do you do that? Well, you take this triangle that's static, you flip on the power switch so that the dimensions can start changing. That power switch is activated by d over dt. These are little bitty chain rules, so the derivative with respect to t of x squared is 2x, as usual, times dx dt, and then similarly for the y squared and the r squared. Now, there is a 2 on each one of those terms, so we can just cancel it. And now we have a related rates formula. We're actually relating 3 rates here. There are 6 quantities altogether, so as long as we know any 5 of them, we can discover the missing value. Now, that's in a generic triangle problem. Our problem's actually simpler than this because one of the legs of this triangle is fixed. It's not changing. So let's rewrite the Pythagorean theorem using our own lettering. The one leg of 18 is fixed, remember? First home to first has a fixed length. So Pythagorean theorem says 18 squared plus r squared equals d squared. Turn on the power switch. The derivative of 18 squared with respect to t is 0. The derivative of r squared with respect to t is 2r dr dt. And similarly over here. Once again, we can cancel the 2's. And so here is the fundamental equation that relates our rates of change. It's got 4 quantities in it. As long as we can provide 3 of them, we're good. Okay. We're asked to find d over dt. Because the prompt in the question said, at what rate is the runner's distance to home changing? So we're being asked for this value. We're being told that we're calculating this value when the runner is 3 meters from second base. Now, if it's an 18-foot base path, 18-meter base path, when we're 3 meters from second base, now we know what R is. Okay, so we know R. We don't know D directly, right? But we can calculate it. This side is 18 right here. At the instant, we are 3 meters from second base. I think that was the original. Even if it's not the right number, it's okay. We can fix it. at that instant, at this snapshot, this length has size 18 meters, this length has size 15, this is a right triangle, calculate D, Pythagorean theorem. Okay, I'm not going to do it, but we know R explicitly. We can calculate D very quickly. We are told that dr dt is some value. I think it was 3, but now I've been saying 3 too many times, so it might have been something else. But fortunately, we are at the very end of the video when my recording disappeared, my recording bar. This happened to me yesterday too, and I thought it was just a fluke, but now I'm wondering if my recording software is doing something weird, because I didn't see anything change. I don't think I accidentally hit anything awkward. But when I stopped talking and looked to go to turn off my recording, the bar was gone. Fortunately, the software was able to recover it, mostly. So sorry for that jarring end there, but we were pretty much at the end of the problem, right? We solved the problem to the point where we have a relationship between two rates. There are 4 quantities in that expression. 2 of them are given explicitly. 1 of them can be calculated without a whole lot of pain, and that allows us to solve for the rate that we don't know. And so have at it. I hope this helped.